Section: Introduction. In this section, we discuss how large language models, LLMs, perform well on many tasks but often struggle with simple numerical problems, like basic addition or comparing small numbers. Previous research has pointed out that these failures might be due to how LLMs represent numbers, which remains an open question. Recent studies using linear probes to predict numbers from hidden representations showed a strong correlation with expected values, but the accuracy was low. This indicates that a simple linear representation does not fully explain how LLMs can perform exact arithmetic operations. We propose that LLMs might operate in a value space for arithmetic, but if that were true, we would expect a normal distribution of errors, which we do not observe in popular models. Instead, we notice that when LLMs make numerical errors, these errors are often far from the correct answer in value terms but close in terms of the digits. For instance, in the addition problem of 132 plus 238 plus 324 plus 139, which equals 833, LLMs are more likely to produce errors like 633 or 823 that are similar in string form rather than errors like 831 or 834 that are numerically close. We argue that this scattered error pattern suggests that LLMs do not manipulate numbers directly in a value space. If they did, we would expect a normal error distribution around the correct answer due to noise in the addition process. However, the scattered errors imply that the models might represent numbers based on their individual digits. To investigate this, we trained probes to extract both the number and digit values from hidden representations. Our experiments with Llama 3.8b and Mistral 7b revealed that while the probes struggle to retrieve the exact number value, they can identify a circular representation for each digit in base 10. Moreover, when we manipulate these circular digit representations, such as adding 5 modulo 10, we can accurately change the number's value. We conclude that the scattered errors in LLMs during arithmetic tasks arise from a fragmented representation of numbers at the digit level. Our findings suggest that while we can recover and adjust digit values accurately, we cannot do the same for the overall number values. This understanding can help us address numerical errors in LLMs, and we have made our code available for further exploration. We also analyze the error distribution of Llama 3.8b on two simple numerical tasks involving numbers from 0 to 999, represented as individual tokens. We find that errors are distributed based on digits, where incorrect predictions are close to the correct answer in terms of string edits rather than value. In our first task, we generated 5,000 addition queries with 7 operands, resulting in sums between 0 and 1,000. The error distribution shows that most errors are multiples of 10 or 100, and about 80% of errors occur in a single output digit, which is often not the units digit. In the second task, we examined pairs of numbers between 0 and 999 that differ by just one digit. The model's job was to identify the larger number. Our findings indicate that errors are spread fairly evenly across the digits, suggesting that the model's mistakes are not significantly influenced by how close the numbers are in value. This digit-related error pattern in both tasks supports our hypothesis that LLMs may represent numbers in base 10 rather than in a linear value space, which we will explore further in the next section. Section Summary. In this section, we explore how large language models, LLMs, struggle with numerical tasks, revealing that their errors are often close in string similarity rather than in numerical value, suggesting a fragmented digit-wise representation of numbers. Our analysis of error distributions in multi-operand addition and number comparisons indicates that LLMs may represent numbers based on individual digits rather than in a continuous value space. Section: LLMs represent numbers digit-wise in base 10. In this section, we explore how large language models, LLMs, represent numbers digit by digit in base 10. We test our hypothesis by setting up experiments to probe these representations. To do this, we train digit-wise probes that estimate a number's value based on its hidden representation by predicting the numeric values of its individual digits. we consider a pre-trained transformer-based language model with multiple layers and hidden dimensions. For each digit and layer, we create a circular probe that predicts the value of a specific digit from the model's hidden representation of a number. We use a training set that pairs the hidden representation with the corresponding digit of the number, mapping each digit to a point on a unit circle. By using these probes, we define a function that reconstructs a number's value from its representation. For each digit, we apply a function that predicts its value, and by combining the outputs for all digits, we can estimate the number's value in base 10. For instance, to reconstruct a 3-digit number, we concatenate the predicted values of its digits in reverse order. We also trained linear probes, which have been used to extract features from LLM representations. However, we found that linear probes were less effective in predicting numerical values compared to circular probes, which aligns with recent findings that some features in LLMs have nonlinear representations. Therefore, we focus on circular probes in our experiments. For our data, we input positive numbers up to 2000 as strings into the model and extracted hidden representations from each layer. If a number is tokenized into multiple tokens, we take the representation from the last position. We split the numbers into training and validation sets for each base. We analyze two popular LLMs, Llama 3.8b and Mistral 7b. Llama's tokenizer includes individual tokens for numbers from 0 to 999, while Mistral uses a single token per digit, which may encourage a stronger digit-wise representation. Our probing reveals that while we can recover digit values in base 10 with high accuracy, we struggle to reconstruct the entire number value. The highest accuracy we achieved was 0.91 for Llama 3.8b and 0.92 for Mistral 7b when reconstructing numbers in base 10. In contrast, accuracy for other bases is much lower, often below 0.2. For example, directly classifying a number in base 2000 succeeded in less than 1% of cases, indicating that the hidden space's direct circular representation is not precise enough for arithmetic. Interestingly, base 5 showed relatively high accuracy, though still below that of base 10. Overall, our results demonstrate that while reconstructing the entire number value is generally unsuccessful, we can accurately reconstruct numbers digit by digit in base 10. This finding is surprising, given that LLMs typically use individual tokens for multi-digit numbers, which do not naturally align with base 10. We also provide evidence that our probes can extend to representations of word form numbers, even without specific training on them. Section Summary. In this section, we demonstrate that large language models, LLMs, represent numbers digit-wise in base 10 by training circular probes to predict individual digit values from hidden representations. Our experiments reveal high accuracy in reconstructing numbers digit by digit in base 10, while direct reconstruction of whole numbers or using other bases yields significantly lower accuracy. Section. Modifying a digit representation modifies the whole number value accordingly. In this section, we explore how changing a digit representation affects the overall number value. Our experiments indicate that models might represent numbers based on each digit in base 10, rather than storing the entire number directly. We conduct a causal experiment to see if Llama 3.8b uses this digit-wise representation during inference. In our experiment, we note that digit representations in base 10 are circular. If we alter a number's hidden representation in two directions, we expect the new representation to reflect the same number but with one digit changed. Specifically, the digit we modify will take on a new value that is the original digit plus 5, adjusted for base 10. For instance, changing the tens digit in the number 375 should yield a representation of 325. To test this, we start with a query like x plus 0 equals, where the model initially outputs x. We then intervene at a specific layer to change one digit of x and continue the model's process to get a new output, which we call x prime. We check if the modified digit in x prime is the original digit plus 5, while ensuring all other digits remain the same. We consider the prediction to be close to the intended result if it is within 1 unit of the intended digit change. We perform this experiment with all natural numbers from 0 to 999, intervening at layer 3 where the model accurately extracts the number before the information reaches the final prediction layer. Our results show that for the hundreds digit, we achieved the exact intended result 15% of the time, with 47% of the results being close. For the tens digit, these figures were 10% and 50%, and for the units digit, 15% and 50%. As a baseline, when using a linear intervention, the exact result was achieved in less than 1% of cases. We conclude that the digit-wise circular representation has causal significance, but there may be additional representations or some information might transfer before reaching layer 3.